Good evening, everyone. I'm Rakhi Yadav, your PMRF teaching assistant for pericyclic reactions and organic photochemistry course, which is conducted by NPTEL and whose course instructor is Professor Sankara Raman from IIT Madras. So, students, today we have come to an end of this course. So, in last 2 to 3 weeks, we are studying photochemistry, right? In last week, we have covered various name reactions on organic photochemistry, such as Norris type 1, Norris type 2, D-Mayo reaction, and many more. So, in this last class, I am going to cover some photochemistry of aromatic compounds. Let's move ahead. Before that, let me revise Wolf rearrangement for you. We are going to solve a problem based on this. Therefore, I am just recap. So, let's have a recap of this rearrangement. Basically, your starting material is alpha diazoketone. Okay, alpha diazoketone. If you write resonating structure of this alpha diazoketone, negative charge will go there and it will form this species, right? Now, when negative charge of oxygen will come back, this R1 will leave as R1 negative. So here it will leave positive charge, and that negative positive will form ketene. So basically, whenever you are having alpha diazoketone, when it is reacted or it is left under heating condition or under photochemical condition, it resulted into formation of ketene. Basically, R1 migrate to this from where N2 is leaving. As we know, N2 is a good leaving group. Yes or no? Now, since we are having ketone, now it can react in two ways. One is our traditional H2O attack, right? It will attack here and will form acid. Another instance in which we use this Wolf rearrangement is in 2 plus 2 cycloaddition. Yes or no? Since it is ketene, it will undergo 2 plus 2 cycloaddition, so for example, with olefins such as ethylene, and it will result into formation of the cyclobutanol. I hope you are clear. Whenever diazoketone is left under thermal or photochemical condition, it led to formation of ketene, which can react in two ways, either nucleophilic attack. For example, here in this case, nucleophile is your H2O. And in another way, this can be used as 2 plus 2 partner. Understood? So, on behalf of this recap, let's try to solve problem number 1 of today's problem solving session. Okay. So, you are given methanol and HMU. Basically, here methanol is solvent and HMU is reaction condition. So, for on first impression, what you are going to do? You know this is alpha diazoketone. Okay. So, in HMU condition, you can also write it as a carbene. Yes or no? When N2 will leave, it will leave here carbene. First, this will form. Correct? Now, since you know that only this bond can cleave from here. So let's say this carbene moves like that. And can I write this bond like this as oxygen lone pair are going to come back, right? So when they will come back, this bond will cleave. Here positive charge will come, here negative, and that will combine with this. For your more understanding, let me write in this way. You can also write this carbene as I have told you in earlier classes also. Carbene can be written as plus for understanding purpose only. Carbene can be written as plus, sorry for that. Right. So once negative charge will go there, O negative will come. But here positive charge will still be there. Why? Negative charge has gone, but positive charge is there. Yes or no? Okay. So you can write it in this way for your understanding purpose. And when it will go this way, or you can draw its resonating structure of alpha diazoketone and directly do. But for your understanding, I am doing like this. This is your O negative, this is your plus charge. Yes or no? Now what will happen? Negative charge will come back and this bond, I am highlighting this bond will migrate here. Okay? And will result into formation of your ketene. Yes or no? So this is your product and at last nucleophile is there. Nucleophile is nothing but your solvent only, that is methanol. It will it will be your CO2 Me. Yes or no? Oxygen lone pair of methanol is going to attack here. Okay, here or here on this carbonyl carbon it is going to attack. This will be this negative charge will be protonated and you will get CO2 So this is your product. So final answer is, sorry for my bad drawing. No, final answer will not be this. You just have to directly join these bonds with CO2 Okay, so this is your final answer. Understood? Basically, it will undergo Wolff rearrangement. You can also say that this rearrangement has taken place via carbene formation. Or in another way, you can take help of this. Just draw resonating form of this diazoketone. Whenever oxygen lone pair will come back, one of the group that is attached to oxygen, one of the substituent that is attached to carbon left to oxygen will migrate onto the leaving group carbon. Okay, and it will lead to formation of ketene. When it will undergo nucleophilic attack, it will form acid if nucleophile is H2O. Moreover, in another case, it can undergo 2 plus 2 cycloaddition. So this was the problem based on that concept. Question number 2 for today's session is, when this nitroanthracene will undergo, or I can say when this nitroanthracene is left under sunlight or photochemical condition, what will be the fate of this? Take 1 minute time and try to solve this. Have you seen before that these two pi bonds and four pi electrons are taking part in any reaction? Yes, we have seen examples where this is acting as four partner in Diels-Alder reaction. Yes or no? Why not these rings? Because among these three rings, if we do chemical reaction in center ring, aromaticity of other two rings will be intact. Therefore, this part is most reactive. Yes or no? Now, four component is there, but where is another 2 pi component? It is not there. And moreover, conditions are H mu. So here it is a possibility of 4 plus 4 cycloaddition. Basically, in this we are getting two products. You have to tell me A and B. Can you see the possibility of 4 plus 4 cycloaddition? Yes or no? And you should also know that 4 plus 4 is even pair. And even pair cycloaddition occurs in light, while odd electron pair they requires heat. Okay, students. So now on behalf of this, can anyone tell me what will be the product? So if you have gone through Sir's lecture, Sir has told that whenever you are having substituent on this middle ring, right, of anthracene, when it underwent a photochemical condition, it gave 4 plus 4 cycloaddition product. And we can see that this 4 plus 4 cycloaddition can take part in two ways. Yes or no? One is head to head, and another is head to tail. Another example in this category is of naphthalene. Whenever naphthalene is given and it is made and it is left in photochemical condition, here also this ring can take part in your 4 plus 4 cycloaddition. Okay, and you will get these four partners with another molecule of naphthalene, right? In one way, it can do 4 plus 4 with these carbon only, and in another instance, what can be done? That ring can be flipped and it can lead to formation of this product. Okay, so before moving to other problems, let me first recap for you photochemistry of aromatic compounds. So, students, as we know, benzene is having 6 pi electrons. So, what photochemical excitation can occur in this molecule? Since benzene is having only pi bonds, right? None of the atom have lone pair, so no possibility of N. Only possibility you can see here is pi to pi star. Yes or no? So, whenever you are dealing with aromatic compounds such as benzene, the most possible transition that can occur is your pi to pi star. So, the primary photochemical process can take part in three ways. First is your this benzene is your S node ground state. It can go in singlet excited state. right? And in that singlet excited state can lead to formation of this intermediate, which will be in zwitterionic form, that is Z. Basically here positive negative charge will involve and give you product. This is one possibility. Another possibility, that from your singlet excited state it will follow that funnel procedure and it can lead to formation of product P. And third is your, that benzene can go to triplet excited state, right? And then leading to intermediate and subsequent product formation. So these are the three states. This is your S node state, benzene, and its resonating structure. Since I have told you, in singlet excited state it can go under two ways. This is first way, that is through zwitterionic form. Now you will see this is our benzene ring, yes or no? Let's say here they are saying it is positive charge, okay? I'm just telling you how they are writing these resonating forms. Positive. Here negative will come, but this will save, okay? Here negative will come and here will be students in class. Which charge will come here? Yes or no? Now, you don't have to push this bond as we used to do in drawing resonating structure of benzene. Here what will form now? So that two charges can be there in our compound or in our molecule. This will form cyclopropane. How? If you cleave this bond as positive negative. So it will lead to formation of. Now you understood how they have come, how they have written this structure from benzene. You first just draw its simple resonating structure, okay? Then, then you have to form cyclopropane. This will be your positive charge, this will be your negative. This positive will combine with this, leading to formation of cyclopropane, okay? And you can see the other resonating forms. How? Let's say uh, let's say here positive charge is there, here negative charge is there, okay? So this time you have to put negative charge outside this system. So you have to first quench positive charge, you will get this type of species. For example, here only you will get the same species, but now you have to put that positive charge in cyclopropane. So what you will do, you will form from here, okay? Here positive charge will wait, you have to put negative charge outside, okay? So you have to deal with this. Let's say here positive charge, let's say here positive charge will come, here negative, and this negative will combine with this, leading to formation of this second zwitterionic form. Understood? Let me explain you from starting. This is your S node state, that is ground state. This is your S1, singlet excited state of benzene, in which they are writing it in zwitterionic form. And third one is your triplet excited state, in which charges are not there but biradicals are there. Br means biradical. They are doing the same thing which we are which we are doing here, but in terms of radical. Okay, and this is your famous Deaver benzene. Okay, now how will you get to know that in which condition what is forming? This is your simple doubt. So basically, when we are having condition of H mu less than 254 nanometer, means vacuum region, it has been found out that in this condition it undergoes triplet excited state from S0 to triplet excite. And we know that in triplet excited state, diver benzene gets formed. Yes or no? So, when your wavelength is less than 254 nanometer, it will undergo triplet excited state and will lead to formation of diverbenzene, and it will undergo reactions that are going through diverbenzene intermediate. When the wavelength is equals to or greater than 254 nanometer, it is going to singlet excited state, which is going through your zwitterionic form. Yes or no? So you can also write this structure as, okay. Now you just have to join these two bonds and you will get your system. What is this? This is your diverbenzene. This is your fullerene, and this is your benzoylene, if I'm not wrong. Okay. So from this intermediate you can get these two. So conclusion till this slide is that whenever you are dealing with photochemistry of aromatic compounds, they can undergo basically they can exist in three forms. One is their S0 ground state. Another two remaining is S1 T1. In triplet state, diver benzene will form. And in singlet excited state, there are two possibilities. Either they can go through fullerene or they can go through benzoylene. You can see that in CH3OD, this deuterated methanol, CH3O negative will be captured by your this positive charge, and this negative charge will be quenched by this deuterium D positive, which is confirming that this reaction is going through zwitterionic form. This is a mechanism for formation of various products when benzene is left in photochemical condition. I hope I am clear till this point. If you are clear, could you please solve problem number 3, that is completely based on the just last topic I have discussed with you. You can take help from this page. Can you tell me when this form will be more stable? Whenever to your benzene any electron donating or electron withdrawing groups are attached. Yes or no? Because those groups can stabilize these charges, right? And diverbenzene will form when there are substituent like alkyl substituents. In that case, it will lead to formation of diverbenzene. But whenever you are having plus M or minus M groups, it will go through your zwitterionic form. Understood? So start solving this question on behalf of that. So students, this is the question from sir's class only. Here, your sodium hydroxide is there. So basically, let me rebuild question for you. This is one first ethoxy, two ethoxy, third. So my question is for you is, which of the marked OAT will be substituted by OH in H mu condition? And your options are ethoxy numbered 1, ethoxy number 2, and ethoxy number 3. D. D option is 1 and 3. Let me again repeat. Which of the marked OAT will be substituted by OH in H mu condition? Let me reframe for you. Which of the OAT will undergo aromatic nucleophilic substitution? So let's start solving this question. This is not your addition elimination question. Okay. Since photo conditions are there, students, as you know that, let's say here, let me draw this way. Okay. In first case, let's assume here electron withdrawing group are there. Okay. So whenever you will write its resonating form, obviously you are going to do like this, because electron withdrawing group will stabilize this negative charge. Yes or no? Now, after making charges, your next mission is to draw its another resonating. Basically, you have to draw its 1,4 resonating form first. Okay. Okay. So it will be yes or no, students. I hope till this point you are clear. Now, our next mission is to form cyclopropane. Correct? Have I drawn it correctly? Anyone who is there in class can you please tell me, is this correct or not? One another possibility you have to figure out that how I have come to this form is that here there is no charge, students. Okay. So in these structures you can see that positive charge is coming at that meta carbon to electron withdrawing group. Okay. In this case, from this case you can also tell these positive and negative charges are meta to each other. So whenever electron withdrawing group is there, they will be meta in this form. So only groups which are meta to this electron withdrawing group will undergo nucleophilic substitution. So therefore correct answer is answer number D. That is 1 3. Yes or no? I hope you have understood. You just have to draw its resonating structure, and in that resonating structure you have to see that positive charge is stabilized in which case. Since here it is stabilized at meta position, so only meta substituents will be substituted by OH. This same condition if you will try in thermal condition, it will not work. Here that is the advantage of your photochemical condition. Then in photochemical condition it has been found out that at meta position they will be substituted by OH. Understood? Okay. So this is your problem number 4. Let me give you hint. This question is type of your Fries rearrangement or freeze rearrangement, whatever you call it. Okay. Let's start solving this question. So, if you know or if you recall system like this, from your previous knowledge, if you know whenever these type of esters are reacted or are left in Lewis acidic condition, they will form two products, right? And another is at para. But this is in your Lewis acidic condition. Here, if you talk about this, you have to see that in H mu condition, this bond is most prone to cleave. Yes or no? So it will form basically here. Wait, let me erase for you. So here acyl radical will form. Now you have to figure out from where you can cleave that bond and you just join. So obviously this condition is only option left to it, and in this condition we will get this. Okay. Okay, I have done one mistake. First, it will form this. Understood? Radical will combine and will give you ketone. And in another instance, that radical, this radical will be quenched by this acyl radical, leading to formation of this. Okay. Now it can undergo your tautomerase to gain aromaticity back. You try other possibility also and check if um, it can give product like phenol. And when you will try, you will found out that in case of naphthalene, this is the only product which you will get whenever you will subject this naphthalene ester in photochemical condition. So this is your final answer, students. This. Okay. So moving ahead, let's study photochemistry of singlet oxygen. So students, if you know oxygen, molecular oxygen, which is in environment, in environment, if you should know that this oxygen is present in triplet form. Okay, its triplet form is more stable than its singlet form. Due to this stability, this triplet can't go many reactions. Okay, so whenever you are dealing with photochemistry in photochemical condition and a photosensitizer, this triplet oxygen will change to your singlet oxygen. Understood? Now this has become reactive for these reactions. Your singlet oxygen can undergo 2 plus 2, leading to formation of dioxetane. This can also undergo 4 plus 2 cycloaddition, your famous Rose Bengal reaction. This can also undergo ene reaction. This is your allyl hydroperoxide. And these are the some additional miscellaneous reaction in which sulfide and your phosphine on reacting with molecular oxygen in singlet state, they can undergo oxidation. So in exam, they can ask you in this way. Okay, first they will give you on arrow they will write, let's say on arrow they will write O2, H mu, or let's say TPP. TPP is nothing but your photosensitizer that will change this molecular oxygen that is being found in triplet state. First, this photocatalyst will change into its singlet excited state. Okay, then let's say you are having diene here on any half. So first it will undergo Rose Bengal reaction. Okay. Now they can do multiple reaction of this. Let's say any reducing agent they have added. So what you will get? Diol from here. OH, OH. Yes or no? So these are some reactions you can get. This is wait, let me write it correctly. So you all should know the photochemistry of singlet oxygen. First take home message from this slide is that on arrow there should be photosensitizer that can convert your triplet oxygen to singlet oxygen, because in that form it is reactive. Another thing, you should know that which different type of reaction this singlet oxygen can undergo. One is your 2 plus 2, then your 4 plus 2, and then is your ene reaction. In total, you should remember these three classes of reaction of oxygen at least. Okay, let's move to next problem. The key reaction that results in the formation of highly substituted phenolic ring of an antifungal agent, mycophenolic acid, is provided below. Could you please tell me a reasonable mechanism for this reaction? If you are solving and if you are trying to solve, hint for this question is formation of ketene, and start solving. So students, whoever is watching this video, I want to tell tomorrow there is practice session of this same course from 3 to 5. In that problem solving session, I'm going to recap all the reactions which has been taught to you by sir, starting from your basic electrocyclic reactions to this photochemistry of aromatic compounds. First, I will recap a small topic such as your electrocyclic. Then we will solve some problem based on that, and then after that we will first read about that topic, then solve some question. In that way, we are going to summarize this tutorial session. And if you are having any doubt, please come to that session with your doubts. I will try to solve them. Okay, let's do this question. So as I've told you, see, this 120 is your thermal condition, right? And your cyclobutanone is there, which is strained. So first, under heating condition, let me change my. So first, under heating condition, this four-membered ring will break, okay, and will lead to formation of ketene. Now you are having ketene, and another component is your alkyne, right? This ketene will undergo 2 plus 2 cycloaddition with your alkyne. Now first question that should arise in your mind, why it is going 2 plus 2 with alkyne, not with alkene? Is there anyone in class? Okay. If you are watching this video, just uh, think why it is reacting with alkyne. So let me tell you, this is your 2 pi electron, this is your 4 pi electron, and this is your dinophile. So this should be quite electron rich. So among alkene and alkyne, alkyne is electron rich. Okay. This is 4 pi electron, this is 2 electron. Okay. First doubt done. Another doubt is, can't it undergo 4 plus 2 cycloaddition? Heating condition is also there. But in this type of reaction, you should know that ketene in heating condition favors 2 plus 2. And after 2 plus 2, it will again lead to formation of this cyclobutanone. Now it will again go electrocyclic ring opening. After that, it will undergo 6 pi electrocyclic ring closure. And after on tautomerism, it will form this phenol. Basically, students, here first let me write here steps. Electrocyclic ring opening of cyclobutanone. 2 plus 2 cycloaddition. Okay. Electrocyclic ring opening. Electrocyclic 4 pi. Electrocyclic ring closing 6 pi. And last tautomerism. That can give you this product. Understood? Yes or no? If yes, let's move ahead. So this is your problem number 6. This problem I have kept it because problem similar to this is given in your assignment. This problem will uh, help you in solving that question. So please try. Okay. Let's start solving. See, whenever in pericyclic question you met with this type of system or this type of system. When you see this, immediately in your mind it should click that it will undergo electrocyclic ring opening 4 pi. Understood? But whenever you are having cyclobutane, you should think of retro 2 plus 2. Okay. So what it will form in retro? Basically this bond will go here and this will go here. And just tell me, can't you get this structure on retro 2 plus 2? Yes or no? And with this you are having this ketone that under photochemical condition, which reaction? Name reaction. When olefin and carbonyl undergoes 2 plus 2 cycloaddition, that name reaction is your Paterno-Bucchi reaction. So you just have to draw that product. Yes or no? So this was the answer to this problem. Okay, this is the last question for today's session. Just try to solve. Let me read question for you. So students, basically in this reaction sequence, you have to tell me intermediate A, okay? And then you have to tell me stereo of hydrogen attached. Okay, one thing that I have done here mistakenly, sorry for that. Let me change here only. Here they are not OMe, they are pH. Let me see if they can be changed here only. Yes, they can be changed. Oh, X. Wait. Yeah, it has been changed. So now tell me, students, in first step, what comes to your mind? Your first hint is removal of methanol. From where methanol can leave? Think. Let's say, students, I'm giving you an out of table example. Let's say any nucleophile is there, okay? And you are having good leaving group here. Okay. So first it will add here. Add here in means nucleophilic addition. And that negative charge will go there and will form your enolate. Understood? Now when negative charge will come back, it will knock off your leaving group. And basically your alpha beta unsaturated system leaving group will be substituted by that nucleophile. In same way which I have demonstrated you right now, you can think of this. Why I am thinking in this way? Because it is clearly visible here that methanol is leaving. Yes or no? So directly you should draw that CH, PH, PH. Understood? I hope you all have got it. This is your nucleophile, right? CHLI, lithium. Therefore, it will be negative. Lithium is your positive. That nucleophile is going to attack here. When oxygen charge will come back, this that will knock off methanol. Now, what reaction you can think of? Can I write this same structure like this? If I am wrong, you can tell me. like this. Now if you can see that 1, 2, 3, 4. These 4 pi bonds are in conjugation with each other. And heating condition is there. So this will be your 4 pi under heating condition. It undergoes cone rotation or disk rotation. It undergoes your cone rotation. Okay. And you just have to form that 8-membered ring. You try to solve by yourself, you will get eight, 1, 2, 3, 4. We are calculating from here. 1, 2, 3, 4, 5, 6, 7. So one carbon is left. Let's draw again. Okay. And one charge will be here. Now students, this is your 6 pi electron system. Okay. And let me tell you, this is your A. Again heating is there. It will undergo 6 pi electrocyclic ring closing, leading to formation of this. Now if you can see, this is your 4n plus 2 system. Under heating condition, which rotation it will go? 4n plus 2. Is there anyone in class? Okay. 4n plus 2 under heating condition. If I have told you, 4n plus 2 photo cone, 4n plus 2 heating this. These substituents are here opposite, if you can see opposite, and this is undergoing this. So obviously they will be cis in product. So stereochemistry of hydrogen will be cis, and after retro 2 plus 2, sorry, you will get this system. Okay, good. So this is all for today's problem solving session. If you have any doubts, you can ask me tomorrow. Tomorrow we are having class from 3 to 5. I expect everyone to join the class. We will revise all the important concepts that sir have taught to you in this NPTEL course. Thank you.